meeting. I'm not sure that all participants already in or not, but let me start with thanking everybody around in this meeting. I myself, Gad Al-Qadi, now president of the National Research Institute of Astronomy and Geophysics, Nariaj. I'm just trying to share a little PowerPoint file. Could you see the screen?
Yes.
Yes.
Okay.
Okay. A brief history about Nariaj, and then I will give you a little introduction about ELOT, Egypt Large Optical Telescope project. Okay, Nariaj has established since 1839 as a small astronomical observatory, then moved from old town of Cairo to another part of Cairo, then to Hilwan here since 1903, taking different names, Royal Observatory, Hilwan Observatory, and then the current name is Nariaj. Although still the most famous and known name is Hilwan Observatory. This on the map, I'll show you Google map later on. Hilwan is here in southern part of Cairo. And this map of Cairo, for those colleagues who haven't been in Cairo, I don't know, Cassiana, Jose, Mark, if he's there. And I would like to invite all of you to join us here in Egypt very soon after this COVID-19 pandemic will turn off. Nariaj is scientifically is 5 departments, 2 in astronomy and 3 in geophysics. For astronomy, the main topic of our workshop, astronomy and telescopes, we have 3 different labs, and currently Hadia Salim is acting president of this department. Different activities Nariaj is doing research and development in different fields, astronomy, astrophysics, solar research, space research, seismology, and many other subdivision and subdisciplines of all these subjects. We have almost 300 researchers supported by almost 350 admin staff. The researcher between full professor, emerite professor, until 2 assisting researchers. And of course, Nariaj is a member of all international organizations and institutions, unions, mainly for astronomy, IAU, and it's all related sub-commissions. Well, for astronomy department, we have different facilities. The main one is Katamiya Astronomical Observatory. In the picture, you can see the dome with a 24-inch telescope, and it was fully operated 1964. While we have another 30-inch Reynolds reflector still in Hilwan, but not working anymore, just for students and visitors. And this is some shots from inside, some picture for the activities Nariaj have been doing for last centuries. Solar eclipse 1882, then Halley comets 1909, and many others, and this contribution to Apollo 11, 12, 13 during 1965, 6, 8, and 9. And recently we have this Katamiya Center of Scientific Excellence in Astronomy and Space Science with different facilities, but it is not the point to discuss right now. Here, a general view about Katamiya Observatory and all facilities around. This inside the telescope, inside the dome. All the stuff here doing maintenance and operation and automation. This telescope started as manual one, and almost 10 years ago it was fully automated with the help of our technical engineers, and they do all maintenance for that one, this 14-inch celestron. During recent 5 years, there was a lot of discoveries by our staff, and as you can see on the screen, 10 variable stars have been recorded with cow names and numbers, and 3 or 4 gamma ray bursts, and all these records. I'm not the one to talk about them, but just give you an example of achievement that Qatamiya was doing until 3 years ago. That's 2 years ago, there was international school for young astronomer with IAU, and last year we had the 4th Arab school for astronomical physics, and we're planning to host the 5th one. It was planned to be this October, but unfortunately, because COVID-19 pandemic, it will be postponed to next year. This together with Arab Astronomical Society, Dr. Zuhair and their colleagues. Well, almost 3 years ago, Egyptian state or the Egyptian government had decided to build a new capital in the east of Cairo. I can show you the map on Google map. This is a map of Egypt. Here is Helwan on the mouse, and this is Cow, almost 80 kilometers. To the west of Qatamiya Observatory, the Egyptian government started to establish a new capital city, which is a main light pollution source. And since that time, Cow started to be unfunctional for scientific observation. It can be used for training and others. Then there was some action by Nariaj and the Ministry of Higher Education and Scientific Research. And finally, there was a decree by Prime Minister of Egypt to make constitution for a committee to be responsible to find a new location for a new telescope for the Astronomical Institute. The committee was represented by His Excellency Minister of Higher Education and Scientific Research, representation by Ministry of Foreign Affairs, Ministry of Defense, Ministry of International Collaboration, Ministry of Fund, and Ministry of Planning. And Nariaj is acting as the secretary of this committee. During 3 years, there was some actions and effort by Nariaj to search for locations for this proposed large telescope. However, as you know or can read from news and media, there was some terrorist attack at the eastern part of Sinai, and that was Egyptian military make some action, emergency action, and control and limit all research activities in some parts of Egypt, mainly in Sinai. Start from end of or early 2019, Nariaj had arranged some trips to make exploration for the potential mountain for this proposed telescope. And I think my colleague Gamal will explain in details about this effort and the preliminary results they have. But mainly 3 mountains here in Sinai and other 5 or 7 mountains in eastern desert of Egypt. You can see on Google map. Then according to the feasibility study, the preliminary feasibility study that Nariaj had established, it was proposed that we finish by this year the site selection for ELOT. And starting from this year, we can start site testing. However, because many, I cannot say problems, but many issues, not availability of the fund, not finishing the feasibility study, and other permission due to some action by Egyptian military in southern Sinai. That one is delayed almost 2 years now. And this workshop, originally it was planned last April. However, also it was postponed because COVID-19. And starting from today, I think this is real action for us to start site testing and selection and testing for ELOT with your effort, all of you, Egyptian staff and colleagues from Morocco, led by Dr. Zuhair, Spain, Jose, Casiana. I'm not sure if Mark is already there or who else together here in this meeting today. That's almost what I would like to say, but before leaving the floor, I would like to assure that Nariaj will do whatever effort and support for this project to come out, considering that the number of researchers in Nariaj and other Egyptian institutions like Cairo University, Al-Azhar University, mainly studying astronomy and related disciplines. And I'm very optimistic that the government will do the full support for this telescope. And at least we got some kind of agreement to support our activities during this fiscal year and coming fiscal year, inshallah. Thank you very much, and really appreciate all your effort. I'm looking forward for the fruitful discussion and recommendation for this workshop. Thank you very much.
Thank you, Dr. Gad. Thank you. Now we will hear Dr. Jamal Eddin. Dr. Jamal Eddin, researcher in astronomy department in Riyadh, will talk about the previous work, the site testing in Egypt. Dr. Jamal. Dr. Jamal. Dr. Jamal.
I'm ready. Okay, can you hear me?
Yes.
Yes.
Was clear?
Yes.
Okay.
Yes.
Uh,
You have 45 minutes.
okay. I'll share my screen first. Okay, can you see the presentation?
Yes.
Okay. Is it clear?
Yes.
Yes.
Okay. So first, my name is Gamal Eddin Hamid. I'm a researcher at the astronomy department. I'm going to speak about the current status of the work that we have been doing for the past 3 years or 4 years in the site selection for the best location to establish the new optical observatory in Egypt. There has been some effort done previously in to find the best places for suitable for establishing astronomical telescopes in Egypt and in the Middle East region, and I will talk about them later. As you all know, the steps for building a large optical telescope depends on first the quality of the astronomical site, and then this depends on first we have to do a pre-selection for the site, and then we perform site testing. Then this should be done before starting the construction. and the last steps will be the installation of the telescope and its instruments. To do this, we are in the first stage, which is the site selection, and there have been some scientific work done before to find the best locations for building large astronomical telescopes in the Middle East and North Africa region, and Egypt in particular. One of them was a paper published in 2014 by Gassoum and Al-Said and Abdul Hafiz in the observatory. Another paper published 3 years later by Abdelaziz Iqbal in the Journal of Physics Conference Series. And there is also a software developed by the European Southern Observatory in order to search for the best site to construct the ELT, the European Extremely Large Telescope. And this software was searching for the best locations all over the world to construct optical telescopes, and it has mentioned Egypt in one of its reports, and I will talk about this later. The first paper published by Gassoum, Al-Said, and Abdul Hafiz in 2014 in the observatory. It was looking for the best astronomical sites, best sites to construct an astronomical observatory in the Middle East and North Africa region using satellite data. They have identified the best location in Egypt to be in southern Sinai, particularly Mount St. Catherine, because it's the highest mountain in Egypt. And they have also ranked it the best location all over the Middle East and North Africa region for constructing an astronomical telescope. They have been using many factors to select the best site on the atmospheric and environmental factors like the air transparency, sky darkness, and the number of clear nights, and the humidity and the temperature profile and the wind, and also the proximity or how near is our light pollution sources like cities and villages. And they have ranked the best site all over the Arab region to be Mount St. Catherine. But unfortunately, the data that they have used in this paper is not accurate because they have considered that the nearest city to Mount St. Catherine Mountain is a small city, and it's about 50 kilometers far. But in fact, as we know here in Egypt, that the closest city is very much is larger than they considered, and also it's a major source of light pollution. That's why we don't consider the results of this paper concerning Mount St. Catherine accurate.
Dr. Gamal,
Yes.
can you switch to presentation mode?
Sorry?
Can you switch to presentation mode?
Okay. Just one second. Sorry, I got out of it because my screen was scrambled. So please give me one second.
في مشكلة دكتور جمال؟
انا بس مش عارف اعمل شير سكرين، ثانية واحدة بس. طيب كده البرزنتيشن واضحة؟
يبقى البيبر.
بيضة؟
البيبر البحث.
بيبر، اوكي.
في حد بيقول لك دوس F5.
F5. تمام كده؟ تمام كده؟
انا شايفه البيبر، البرزنتيشن اللي قدامي، شايفه البيبر ولا هي انت حاطط البيبر من داخل؟
انا حاطط اول صفحه من البيبر.
اوكي.
كده تمام؟ تمام. اوكي. Okay, I will continue.
Slide.
So this is about the Gassoum Al Said and Abdul Hafiz paper in 2014. One other paper that discussed the best locations to construct an astronomical observatory in the Middle East and North Africa region also was published in 2017 in the Journal of Physics Conference Series. It used also satellite data, and for this paper, they have considered other factors, many like the elevation, the cloud fraction, light pollution, the perceptible water vapor, aerosol optical depth, relative humidity, and the Richardson number and the diurnal temperature range. They have identified, as you can see in this figure, the best location in Egypt is marked with a star, which is in the far corner of the southwestern area of Egypt in the Western Desert. It is a mountain close to mountain Al-Awainat mountain, which is about 1,050 meters high, and it's very far from any city, and it has completely no light pollution sources within the range of 300 kilometers. This was the major factor that they have identified this source as the best place. But we know from the meteorological data for this region in Egypt that it is severely their problem.
Yes, the slide don't.
Slide can't change.
Can't
change. Change the slide.
Stop sharing your screen and do it.
Okay.
Please.
Do it again. Okay.
Yeah.
Okay. Okay. Now.
Yes.
Now.
Yes, it's okay.
Yes. Okay.
So, for this paper, they are in this figure, they are marking the best locations to construct an astronomical telescope by stars. So the best location they identified in Egypt is this star, which is located in the southwest corner of Egypt, in close to Al-Awainat mountain. So they have identified a mountain which is about 1,050 meters high, but and it's very far from any city. And the closest city, which is a very small city, is located about 300 kilometers away. And this region is very dry, and the elevation is not very high, but also we have another major problem about this location is that we know from the meteorological data that we know about this region is that it is heavily affected by severe sandstorms in the months of April, May, and June every year. And these heavy sandstorms are as you know, is not doesn't make it a suitable region to construct astronomical telescopes. And also, This mountain is very difficult to get to in order to do site selection and the preliminary site test. One of the important things that have been done about the availability of Egypt to construct large astronomical telescopes is that there is a software called Fry Owl developed by European Southern Observatory in collaboration with the University of Zurich in Switzerland to select the best site for constructing the European extremely large telescope, which is, as you know, have started construction now, and it's being built now in Chile. Before choosing to build it in Chile, they have searched for the best sites all over the world, and they have, in one of their reports, they have mentioned that Egypt and the Sinai Peninsula, including the whole area surrounding the Gulf of Aqaba, has been identified as possible candidate region for large telescope projects, because this an area which remains largely exploited to date. Several mountain peaks above 2,000 meters elevation in this region. Summertime cloudiness in this area is the lowest of anywhere in the world, and integrated water vapor values at 700 hectopascals may approach those of southern Atacama in Chile at the same elevation. So, according to this report, there are many excellent places to construct a large optical telescope in Egypt, and this is one of the things that are we are trying to get the best of these sites to construct our upcoming Egyptian very large optical telescope. The first efforts that have been done by our department to choose the sites, we have made many field trips to examine the mountains and look for the best site to start constructing the telescope. The first trips were concentrating mainly on the determining the accessibility of the mountains. Can we build? If there are a large plateau on the mountain that we can construct buildings on, and what is the how about the terrain, and how is it difficult to climb, and is it difficult to construct a road to it, and how far is it from the closest city, to get an idea about light pollution, and how easy will it be to get to this site. First, we started with some trips to the southern Sinai. The first two trips, they have investigated the 7 mountains, including Shumar, Abu Rumel, and Al-Junna mountain and Ad-Dalal, which are 2 of the best candidates, Al-Junna and Ad-Dalal, and along with Ar-Rujum. And they have identified that these sites are good candidates, but they need more investigation, which I will talk about later. Then after that, we have been given the government has agreed that we can investigate Mount St. Catherine, which is the highest mountain in Egypt, which is about 2,500 meters high. They have agreed, the government has agreed that we can use it as a potential site for construction of the telescope. But when a team of researchers from the department have visited this mountain, they identified that this mountain is very there is a very large light pollution in that site, because the city is very close, and there are many villages surrounding the city which make a large light pollution on the summit of the mountain. And we have also in that during that time made the first visit to investigate the mountains in the eastern desert of Egypt, in the Red Sea region. because the highest mountain in Egypt are located in two areas, in southern Sinai and in the Red Sea region. We have in that trip to the first trip to the Red Sea region, we have visited one of the largest mountains in that area, which is Hamata Mountain, which is about 1,900 meters high. But it is a very difficult mountain to climb. I was present at that trip, and we couldn't climb high on that mountain. We took some data, and also it is a good candidate because the nearest city is about 200 kilometers away, but it is a very difficult mountain to construct telescopes in. And also later, the government didn't give us a permission to visit it again because they don't identify it as a suitable site for other factors. We have also visited some small mountains in the eastern desert, which we identified that they are not suitable for construction of a telescope. This is a map for the southern Sinai, Egypt, and we can see the Junna and Ad-Dalal mountains. They are close to this pinpoint. They are very close to each other. I think the distance between them is about 10 kilometers, and they are located in the southern Sinai. But we haven't been given a security clearance to visit southern Sinai again. So we are waiting for this to do some more investigation about this region. This is a table showing some of the highest mountains in Egypt and their light pollution and sky quality meter values from the light pollution maps at these mountains. You can see here the green is the Mount Zubair, which I will talk about later, which is one of the best candidates at this region. Its maximum brightness is 21.6 magnitudes per arc second square. And the average is 21.93, and the minimum is 21.98. It is about 1,233 meters high, and it is a very good candidate, at which I will talk about later. Here in this map, you can see this is the mountain that the paper in 2017 was talking about. The Abdelhafiz et al. Gassoum et al. Paper was talking about. It is, as you can see, its light pollution data is very good, but it's not a very high mountain. And also, as I said, the weather conditions there are very bad. These are the southern Sinai mountains at the bottom here. As you can see, the maximum brightness in Mount St. Catherine is about 19.12, and maybe this is satellite data, so maybe the situation on the ground is different from that. So and also this also you can see other mountains in Sinai. Ras al-Junaina, which is I think close to Rujum, and also Al-Ajma, which is very close to Ad-Dalal. So these are in the range of 21.8 or 21.9. So they are good candidates in terms of light pollution. And also you can see here other mountains in the eastern desert, like Hamata, which has a good light pollution values. And also there is the highest mountain in the Red Sea region, which is Shaib al-Banat, which is about 2,000 meters high, but it is very close to a large city, which is Hurghada. So the light pollution there values here are not suitable for constructing a large telescope. In the next step for looking for the best candidates, we have used some of the topographic maps and the light pollution maps, and as you can see here, these are the locations of the best places for in terms of light pollution in Egypt, which are in the very far south of Egypt, in the eastern desert, and also in the middle, in the South Sinai, which is the region of the mountains I talked about, and in the west, which is the region where the paper of Gaston et al. Have identified as the best place. And we here is also the location of Mount Zubair. As you can see, there is a circle of about a radius of 40 kilometers that there are no sources of light pollution in, and this is the location of the mountain. And as you can see here, its light pollution values are very good, and I will talk more about Mount Zubair later. We have also used the FryOwl software in determining the best sites. We have used it to determine the major factors of the selection of telescopes, like the cloud coverage, air temperature, perceptible water and wind speed, vertical velocity, wind aerosols, to study two regions, because the resolution of the spatial resolution of this software is very low. So we can't specify certain mountains to study, but we have looked at two regions in the eastern desert, which the two regions are Western Hurghada and Shalatin region. Shalatin region is in the very far south of the eastern desert, and West Hurghada is a region where many mountains are located to the west of the largest city in the Red Sea Governorate of Egypt, which is Hurghada. There are many high mountains there, including one of them is the Zubair mountain, and Hamata, and Shayb al-Banat, and Maqras, Qattar, and these are the best, and Samyuk. These are the best sites that we have investigated more later. The data that we have obtained from the FryOwl software, this, as you can see, the 2-meter air temperature on average along the whole year. Here is the Shalatin region, and this is the West Hurghada region. So on average, the whole year mean is for Hurghada is 296, and for Shalatin is 302. And the total cloud coverage, as you can see, the whole Egypt, the total cloud coverage over all Egypt is excellent. The best is in the south more, and in southern Sinai also here. And here the eastern desert area, all of it has very good, very low cloud coverage, which is on average between, there's no large difference between Shalatin and Western Hurghada, which is two very excellent regions in the terms of this factor. The perceptible water there is a slight in Western Hurghada, it's somewhat better, and on average here, as you can see, and also in the wind speed, they are close, but Shalatin is somewhat better, but these are the data on average over the whole year. And this is the wind aerosols content, and we can see also that Western Hurghada is slightly better. And also the mean vertical velocity, Hurghada is a little bit better than Shalatin. After that, we started doing field trips again, but equipped with some instruments. The instrument that we have used in this stage is the sky quality meter, and then to determine the sky brightness of the regions that we are visiting, and an all sky camera, and also a small 8-inch celestron telescope equipped with an ATIC CCD camera. The first visit that we have done in this area, in this stage, is visiting 3 mountains in the south, 2 in the Shalatin region, which are Mishbeh and Natitiai, and 1 in the Western Hurghada region, which is Samyuk. There have been a paper published about the results of this trip. I will talk about the paper later. Our colleagues who have done this trip have identified that Mishbeh is a good candidate because it has a road, a dust road, and its elevation is about 15 meters. They have climbed to an elevation of around 1,186. These are the coordinates of the mountain, and they have got a sky quality meter readings of about 22.03 magnitudes per arc second square, and they have also visited Mount Natitiai, which is close to Mishbeh. So Mishbeh blocks a large part of the sky from Mount Natitiai, and they have got sky quality meter readings of 21.57 magnitudes per arc second square. And they have also visited Mount Samyuk in the western Hurghada region, and they identified some light pollution sources from Hurghada and Safaga cities, and from some nearby oil rigs in the sea. Unfortunately, some meteorological data identified that the Shalatin region has a very high humidity, so it's not a very good candidate for constructing a telescope according to this data. So the committee for the telescope have excluded Mishbeh Mountain from further investigation. This is the paper published in Astrophysics and Space Science in 2019, Abu Shleib et al. It's titled Preliminary Site Selection for an Observatory in the Egyptian Eastern Desert. The main results for this is that there is a very good light pollution, very good, that the Mishbeh mountain is very good in terms of light pollution, and it is very far from any sources of light pollution. And Samyuk is there is some light pollution in Samyuk, and it is not they didn't identify it as a good candidate. This is the location of Mount Samyuk in the Western Desert. This here, this is Hurghada. And these are some other mountains that I will be talking about later, like Qattar and Zubair Mountain. And this is how far it is from the shore of the Red Sea and from the major city of Hurghada here. The second trip that the department made for in the Eastern Desert is for Mount Zubair. It's 1,1381 meters high, and there is a large plateau on the top of the mountain, suitable for construction of telescope buildings. I was personally present at this trip, so I can talk in more detail about it. So we have climbed to about an elevation of 1,200 meters. It took us about 7 hours to get there with our equipment, and we have camped all night there to check for the light pollution. We didn't identify any.
Dr. Gamal, sorry, Dr. Gamal.
Yes.
Dr. Gamal, sorry. You have 3 or 4 minutes.
Okay, I will be quick.
Available for our discussion or question.
Okay, I will be quick. I'll go through the next slides very quickly. We have identified that the sky quality meter readings for this region is on average 22 magnitudes per arc second, and the all sky camera images we have obtained show that this is a very good place to start site testing. We have also visited a region of that contains 4 mountains which are very close in the region of radius about 10 kilometers, which are Disa, Samyuk, Qattar, and Thelma. And we couldn't climb to the top of the mountain, and the sky quality meter readings at about an elevation of about 890 meters were 21.8, and all sky camera images were good. So we identified this region as a good candidate, but it needs more studies. These are the sky quality meters brightness on Al Zubair mountain, and at the beginning of the light there was some effect from the Perseus arm of the galaxy, and then the readings got very much better through the whole night until the dawn. These are from satellite data, the sky brightness versus distance at Zubair mountain, and you can see it is very excellent about a distance of about 50 kilometers, and then about 60 kilometers. This is the city of Hurghada, which causes a very high increase in sky brightness. As a conclusion, I can say that Zubair is the first candidate for us to start site testing. The regions of Al-Junna, Al-Rujum, and Al-Dalal mountains in Sinai need more investigation, and they are very good potential candidates, but we didn't get security permission to go there. And the Qattar, Thelma, Samyuk area will need some more investigation to determine if it's good for site testing or not. And thank you.
Thank you, Dr. Gamal.
Yeah.
Now, anyone can need to ask Dr. Gamal or discussion or anything. Talk to Dr. Gamal. Everybody can hear me?
Yes.
Any question for Dr. Gamal?
Yes, check your hand if you want to ask a question.
Can I make a quick comment? Nidal Gissoum here.
Okay, can hear you.
May I ask a quick question?
Can hear you. Go ahead.
Yes, go.
Okay. May I?
Yes, yes.
Yes.
Okay. Sergio Ortolani speaking. Well, one point is when you measure the sky brightness at different altitudes and different conditions. Sometimes we may have a peculiar combination of a higher extinction and darker sky in a pristine place, simply because part of the natural radiation coming from the sky is extincted. So I saw in some cases that higher altitude had a slightly brighter sky, but this is part of the nature, because when you go very low, you have just more extinction. Do you agree with it?
Sorry, can you repeat the last part again?
So my point is that if you realized that in some cases, in pristine, in good conditions, with a low pollution, you may have brighter skies at higher altitude, simply because the extinction is lower.
Yes. Yes, it's true.
Okay.
Well, I'm presenting. These are just preliminary results. We are trying to get the best candidate places that we want to do a site testing for it. It's not; these are not final. But also, I wanted to comment that we wanted to do some more investigation for the potential sites using the telescope that I mentioned. But unfortunately, the telescope is very light, and we couldn't get it was extremely difficult to get a heavier telescope with us to the top of the mountain, so that we can make a scan of the whole sky and make to get the overall sky brightness. And but the telescope, because it was very light, the wind didn't make it stable enough so that we can start investigation. Start taking images. And this was one of the problems that we have faced in these selections. But I agree with you that about your point.
May I ask him a question?
Okay.
Yeah, it's Andreas Hähnel here. I have a question about the SQM. Have you used different instruments or just one? Because my experience is that some of the SQMs have great differences, and so the absolute value of SQM is not really reliable.
Well, the same SQM was used in all trips, in all mountains. The one that we used in Mishbeh and Natityai and Samyuk is the same one that you have used in Zubair and the other. It's the same instrument. We didn't use different.
But you have not tested it with others to see if there is perhaps an offset or something like this?
No.
Okay, thank you.
Thank you, Dr. Gamal. Any other question?
Yes, may I say something? Well, thank you very much for referring to the papers we did several years ago. I just want to put some caveats to the paper so they are not misunderstood. Number one, the first paper from 2014 was not based on satellite data. This was based on online available data, including, for example, light pollution was taken simply from Google Earth data, which essentially measured distances from cities and towns and labeled them as small city, medium-sized city, large city. So that was all we could do from, and by the way, the two other co-authors of mine were students, undergraduate students. So that's the only thing you can do if you want to cover the entire MENA region with whatever available data is there. So if Mount St. Catherine was labeled in Google Earth as being 40 kilometers, 50 kilometers, small, medium, large, that's the available data that we could use, and that's all we could use. The second paper that you referred to, Abdul Hafiz et al., where I was also, Jilali, anyway, the second paper I was a co-author with, that one indeed used satellite data. But there's two things we need to understand about satellite data. Most of the parameters, and you mentioned a number of parameters that we try to take into account, all those physical factors, have very bad resolution. 1 degree by 1 degree meant 100 kilometer by 100 kilometer. We said this very clearly in the paper. We repeated it in the conclusion, and we said this limits the applicability and the conclusion that can be drawn. And we said very clearly in the conclusion of the paper, we must supplement this work with in situ local seeing measurements. Otherwise, we cannot rely on just say, there's a star here, there's a star here. Because the satellite data is very limited. It is not even, how do you say, confirmed by local measurements in different places. And of course, we had no knowledge and no understanding of sandstorms, for example, or the availability of roads, or or maybe military installations or anything like that. So the satellite data could only give us a very, very wide coverage of the entire MENA region. And the last comment I want to say is, before those two papers, I had published an article in Nature titled "Time for an Arab Astronomy Renaissance." And the major conclusion from that article in Nature was that the Arab world and the entire MENA region is way behind on construction of observatories. And in order to restart astronomy in this region, where astronomy used to be a great science for centuries and centuries, we need to put serious effort in constructing large or medium-sized telescopes or observatories. And in order to do that, we need to start identifying good locations. Now, in my little place where I live, I cannot do seeing and sight measurements throughout the MENA region. All we could do was use satellite data and point people to say, can you please go here and go there. So I am glad that you are referring to those papers and that you are paying attention to them, but those papers should not be taken too far in their conclusions and then criticized because they said Mount St. Catherine, or they said this place in, for example, Wadi Rum in Jordan, or the Hogar place in Algeria. Only local in situ measurements of seeing can determine the best locations in every place. And that paper was certainly not meant to tell Egyptians where the best Egypt location should be. Thank you.
Can I comment on that? Sorry, can you hear me?
Yeah,
Can I
yeah.
comment on that?
Yes.
Okay, thank you for your comment. I totally agree with you, but I wanted just to say that we have used your papers as a starting point to look for suitable locations, and we don't mean with the points I have said about that the Mount St. Catherine is not a suitable location, or that the Mount Uwainat is not a suitable location. I didn't mean to criticize the paper. There is a good effort done in this, and we totally understand that we can't take this as granted, and we have used it as a starting point, and we appreciate the effort done in them. But with my comments, I wanted to mention that in the future, if you see someone referring to these papers, I wanted to point out that if in the future someone has referred to these papers to say Mount St. Catherine is the best location, or Mount Uwainat is the best location, I am trying to comment that, okay, these are good locations, but we have excluded them for these reasons. That's why. And also to show that satellite data, as you have concluded, are not enough, and in situ measurements have to be done. That's it.
Thank you, Dr. Gamal. Any other else? Now, the next speaker, Dr. Cassiana Fenoun, Institute of Astrophysics in Canary Islands.
Hello.
Hello.
Well, I'm trying. Thank you very much for for thinking that I can tell you something useful. I will do my best to do so. I am just going to share the screen. Wait a second. Here I am. Okay. Can you see it?
Yes.
Yes.
Okay. So thank you, Adia. As I said, thank you for thinking that I have something to say that may be useful for you. I will do my best. And please, if you have any questions, stop me when you want. So what I'm going to tell you is just in brief, the story has taken long, which is the one for site characterization that we have carried out here at the Canary Islands. But as you know, we have two observatories, one in Tenerife and the other one in La Palma. And it has been 40 years since we started. And in the way, we have implemented a number of tools, a number of instruments. We have tested some of them. We have identified those which are not very useful, those which are, let's say, a pain in the neck because they are too complicated to handle. And we have also learned something that can be useful to me for your search. And that's what I'm going to emphasize. Here, wait a second. I don't know how to do it. Wait a second. Okay. So this is just to show to you, oh, sorry. Pardon. Okay. This is just to give you some idea of the history of the site. So here you see that we started in 1978, right? And then at this very beginning, we started doing some site testing, but it was in 1989 in which the law protecting the sky was established. This is very important because you have mentioned, I mean, our colleague Gamal has emphasized the importance of a dark sky. This in the Canary Islands is possible thanks to a law. So this is just a recommendation. Wherever the site you decided, please take care, be sure that this is not going to be spoiled in the future, that you have to protect in advance. No matter how dark it is now, you have to be sure that it will be dark in the future. And that needs a regulation. Otherwise, you may be having to move the observatory in the future, the same as you are doing now. So this is important to have in mind. So these are the two sites I will talk to you about. I mean, the place where I work. I am the responsible of the site characterization team since this period, since 1990. I'm also an astronomer, so I characterize the site for doing astronomy and work on galaxies. Something which is important, which is in this sketch, is that to us, the sky is a natural resource. So you need to characterize to be able to decide how good it is, as you are doing now. But it's also very important that the site characterization needs to be, it cannot stop whenever you decide the site, because you need to learn more and more in order to be able to get the most from the telescope you are going to install. So the site characterization is not only needed for searching a site, but also for exploiting the site to get the most from it. So this is, again, a sketch in which I want to emphasize that we have been continually implementing new instruments. Then we have new requirements. We have had new challenges. And because of that, we have done research in atmospheric optics. We have identified different parameters. We have identified different techniques, instruments. We have defined instruments for continuous monitoring. And all that is also useful for supporting the telescope's operation. When I say supporting, that you are thinking on a big telescope, I didn't hear what is the size of the telescope, but I assume it is bigger than 2-3 meters. And then if that is an important investment, you need to be able to use the telescope when the time is the best for the program. I mean, when you have the better scene, you will have the telescope going for the programs which are more demanding. When you have the better transparency, you will have the telescope working for those programs, scientific programs that require the most transparent atmosphere. And for that, you need to be able to monitor all these parameters. All I'm saying is that no matter what you decide to go, and no matter what you decide to instrument to do, you have to keep them running in the future if you want to have a good performance of the telescope. This, for instance, is something that leads us to do different things. I'm showing the site characterization at the very beginning. We did things, very basic things. I mean, I'm not going to go into this, it was a long time ago. But yes, I want to say that, for instance, when the GTC, which as you know here is the image, is the 10-meter telescope we have at the Canary Islands. With this telescope, not only the big telescope is the issue, but all the instruments that come with it. This, which I have in the view graph, are the near-infrared and mid-infrared instruments that we have at the telescope. So as soon as you have an optical telescope which is also able to work in the near-infrared or the mid-infrared, you need to have an atmosphere which is also able to cope with this challenge. And this is not the same as the one for optical astronomy only. So in particular, even if the telescope is an optical telescope, it works in the mid-infrared, near-infrared domain. And therefore, we in the site testing group had to start measuring things which was important for taking these measurements. The same, every time we have been involved in a new campaign, it takes us to develop new tools. So this is the TMT, that as you know is the telescope, the American telescope, which is now, I mean, decided where to go. And you know that the Canary Islands is a possible option if they cannot go to Hawaii. And because of that, we need to implement new tools and new instruments. The same for the Cherenkov, which is an array of instruments. We need to have a different performance. I mean, it's not just the classical thing. The same for the solar telescope. We need to measure different things. All that I say just to tell you that along the time, we have had to implement new things because we had new challenges. And I think this will also be your case. And what I'm going to tell you is just the summary of some of them. So here is just the sketch of the different instruments. Here you have swear, here you are. And this is a mass DIM, which is an instrument that was designed by Victor, who is here, that was for the ELT campaign. This is a SIM monitor. Here we have an instrument which is a SIDAR, which works at the four sides of a telescope to get the turbulence profile. These are the typical SIM monitors that we developed after Marc Sarrazin and François Rodier design. This is Jean Bernin implementing new instrument. This is the receiver of the antennas of the GPS signal. This belongs to the geophysical department, and this is important. I will tell you more. So basically, we have implemented a number of instruments, from radio-sounding balloons, SIDARs, automatic weather stations, MAS, ASMONs, and now we are more and more on new things which don't require to implement physically new instruments at the site, but to use things which are available to everybody. This is the GPS, satellite database, and climate reanalysis. This climate reanalysis, a long time ago, when I first started working with Marc Sarrazin, he was proposing the use of soul system. And at the end, I was quite reluctant to use that. And now I am a fan, because I think this is very powerful and something which for sure is going to be very useful for your task. This is just some early key results, just emphasizing that a time ago it was huge. It was very demanding to do what we call intensive campaigns. At ISO, they have performed. At the Canary Islands, we have done that. At Mauna Kea, they have done such a thing. But these campaigns are very, very expensive, very useful, very important, but very time consuming. For instance, in this particular case, the sketch I showed to you is something which is very important. In particular, if you think on implementing AEO system in your telescope, is that you need to know where the turbulence comes from. So you have the different layers in the atmosphere, you have the telescope, you have the surface layer, you have the boundary layer, the free atmosphere, and all that you have to sample and to see where in the atmosphere the turbulence comes from, because like this you are more able to implement the correction of the turbulence with your system at the telescope. I don't know, because maybe this is too soon, if you have this plan for the telescope, but if you have the plan to have a telescope which is not only big, but also a telescope which is also going to be able to compensate the turbulence of the atmosphere, this sort of measurement you need. From this measurement, you can know this sort of result, which is the percentage of the turbulence that comes from the different layers. As you know, if the turbulence comes from the free atmosphere, at the end, what happens is that the so-called the isoplanatic angle is smaller. And then if the isoplanatic angle is smaller, your capability to correct is smaller, right? So you need to know where the turbulence comes from in order to be able to do that. Again, I don't know if you have that in mind, but if you do, you have to think on how to measure that. This is just a summary of what can be named the image quality, which is very important. If you have a large telescope and you want to get the most from the atmosphere, you need a site which is sharp, which is very, very stable, with the atmosphere which is very, very stable, with a good image resolution. So this image resolution, there are a number of parameters like the coherence time, the isoplanatic angle, the coherence radius, SIM. All this is something important if you have and you want to have a telescope with a good image quality, and you want to go to projects, to programs in which you are going to be able to measure, for instance, distant galaxies, planets near stars. So if you want to go for projects, for scientific projects, we require to be able to resolve different images in the sky, you need to go for a very good image quality. So if that is the case, this is a parameter that should be somehow emphasized and measured accurately. So this is the summary of the things that we should know, or you should know, in order to be able to decide. Again, this parameter, this list, can be more or less important depending on what telescope you want to build, on what is your scientific aim. So obviously the first are very basic, are the minimum ones. So you need to have a transparent sky with no clouds, a dark sky. You need to have a site with a reasonably good meteorology. You need to be sure that you are not going to suffer from variations in short periods. Then you have to analyze along statistics. So you have to measure. All this, I think that Sergio will talk about later, so I'm not going to say much. And below there are more technical things, but equally important. Seeing, as I said, and the structure of the atmosphere. There, I must say that probably Mark Sarrazin will tell us more because they have been pioneers in that. We are doing also a lot of work on this issue, but I think Mark will say. But there are also something which is important, which is the precipitable water vapor. I think that Gamal has already mentioned that, and this is important because it gives you the power of your site to do infrared astronomy, which I think that is important. I mean, I think you should go for that because only doing infrared astronomy, you can study the universe in earlier epochs. And therefore, when you say an optical telescope, I mean, the title of your project is EOLT, Egyptian Optical Large Telescope, but then I understand that by optical, you are generous in the definition. And when you say optical, you are also thinking in the infrared. So the precipitable water vapor is crucial too. Also important is the ground wind speed and direction, and also the vertical profile, because it has to do with the quality of the observations. And this last thing, I don't know if you want to go for that, because the sodium layer is something which is also interesting, in particular, if you think on the use of sodium laser stars, which I don't know. This could be maybe for the future. And then I will just emphasize the thing we have been working more recently, which I think can be useful for you. As you should know, Canary Cam is one of the instruments for the GTC, for the 10-meter telescope. This is the wavelength range that this instrument works. So it's in the mid-infrared. We also have a MIR, which is a name which is familiar to you, to us as well, which is in the near infrared, in this range, right? And so for these two instruments, the amount of water vapor in the atmosphere is crucial. And therefore, we need to know when the precipitable water vapor is low enough for working with this instrument, because the telescope, the GTC, work in the so-called flexible scheduling, so they decided when to go for the infrared observations, depending on the amount of water in the atmosphere. And for that, we develop a number of tools that I am trying to explain it to you here. The nice thing is that this tool for deriving the precipitable water vapor just use a receiver, which doesn't have to be operated by no one of us. It is a geophysical station which just measure the delays of the satellite signals. So what we have done is to use the radio soundings that we launched a long time ago, measuring the water vapor with balloons that we did with Jean Bernard and colleagues. And then from these radio soundings, what we did was to calibrate the error from getting the tropospheric delays from the receivers of the satellite signals. So the receivers, that when you have a signal from a satellite, the delay is due to the water, is partly due to the water vapor that is in count. And because we have a number of satellites that the system has to track, you are able to define this delay on different directions and to get an estimation of the amount of water that is producing this delay. So we have been working on that for a number of years now. We have been comparing this result with the radio sonde that we launched, and now we know that the errors is very low, and we are able to say here, you see the plot, the values in real time of the precipitable water vapor. And the accuracy is very good. We are able to measure the water vapor above 1 millimeter. Below 1 millimeter is very difficult. and the error is less than 10%, with a calibration with data measuring directly the water vapor. With that, we did something which maybe is also useful for you, or maybe also useful for you. We use the weather research and forecasting program, which, as you know, is available. It's a numerical model. It's available for everybody, so you can use it. And with that, we implemented something which we call FORO, which is forecasting the observatories. What we did was to forecast the water vapor in up to 72 hours temporal window. Why? Because to be able to change the instrument at the GTC, we need one night, 1 day. So we need to be able to say 1 day in advance whether tomorrow the water vapor is going to be low enough for using the infrared instrument. And so that we have done, and so we have it implemented. So the nice thing of this forecasting is that you can do also what we call now a nowcasting. So that means that if you have all these signals, let's say from 5 years ago, you can construct your database on water vapor values of the site you decide. So this is able, this system is useful to produce or to compile a good database for make your analysis. This is a bit too technical. This is just to emphasize that something that was, I mean, in the first talk, somebody, I think it was Michal, emphasized the need of accuracy. He mentioned the fact that the satellites, the spatial resolution is very poor. All these things are very important because fortunately now we have more and more resources which are not only useful, but quite, I would say, very accurate. And I think we can go for them because these are available. And so this is just to tell you that this is the estimation. We have done the error estimation for this technique, as I said, using the GPS delayed signal for retrieving the precipitable water vapor. Then this is the calibration. We have done a calibration of the weather research forecasting system for the water vapor. We have optimized the forecasting. Here you see in this in the plot to the right, you have the real values in one color, which I cannot read, one of them, and the forecasted values in the other color. So this is the red and the green. So you see that the match is excellent. So the forecasting is very accurate. And because of this, as I said, you can do the nowcasting. You can take the numbers from 3 years ago and construct your database. I think this is a very powerful tool. With that, you can have some research which are useful, which is the water vapor value and the trend. Again, the tendency along the GA is very important. And for that, because you cannot measure, I mean, when you start a campaign as we did in the old times, is that, for example, now, you should need to be measuring 3, 4, 5 years in order to be sure that there are no variations in the time, and that is a lot of time. But that you can do backwards now. And this is very, very interesting. For instance, here I show to you the result we took from 10 years of this precipitable water vapor using the data from the signal taken time before. And like this, for instance, in this case, we had something which is very interesting, which is also very important, which is to know what is the behavior of your site, of the site that you are going to select. For instance, in this case, you see that we have a cycle in summer and winter here in the Canary Islands. That is important because there you see that the value is higher in summer, is lower in winter. Therefore, like this, you can program that it's better to use the infrared instruments in winter time because the atmosphere is going to be drier. Right? So this is the sort of thing that we need to know to get the most, not only to identify the site, but then to be able to exploit the site at its full capability in the future. Here, for instance, this is just something which is also very, very interesting, and it's also related with the comment about the satellites and the things which are not accurate enough, in particular in the spatial resolution, the spatial footprint of a of a technique has to be enough to sample the site you want to sample. This is just the map of La Palma and Tenerife. The islands are very small. I mean, I don't know if you have been here. You are invited to come here whenever you can. But just to tell you that the islands are very small. I mean, the sizes here is less than 100 kilometers. Therefore, the satellite footprints of the images of things which are too coarse are not good for us for studies. And because of that, we have been emphasizing the need for a good spatial resolution and also vertical resolution for whatever analysis to be done, in particular for our sites. And it may also be the case for yours, because as Gamal showed, you are in different places which are local peaks. We need to be resolved in order to be sure that the results are good and for this particular place. For example, as I said, this is the map of the precipitable water vapor, and there you see what is in red is the sea, and then you see that the lowest values, which are in the blue, are right at the peak of the island. Here you see the isocontour of the island, and then the sea level is not so dry, and you have to go to the peak to have a dry atmosphere. Again, this is possible to do right if you have a good spatial resolution. Otherwise, it will be all a mess. I have done together with my colleagues. I mean, all what I have mentioned before was the topic of a PhD of one person, Julio Castro Almazan, who is working with me. And at the same time as he was doing the site testing, he did a PhD on this issue. And then he did that for us for this meeting, just to see how useful can be this system that we have implemented for your case. So this is the global navigation satellite system, permanent network in the world. This is list. As you see, unfortunately, the place we are interested is quite empty. I mean, there are no such a thing. Here we are at the Canary Islands, and there we have several such stations. But here we don't have such a thing. So he has searched for other networks that can be useful for the retrieval of the precipitable water vapor. And here you see at Morocco, there is this agency. At Algeria, you have this, and there in Egypt, you have a possibility that is listed here. And then this is the course map. It's a non-stop continuous operating reference system station in Africa. You have a number of such stations there. And then in summary, for these particular parameters, which is the PWV, the precipitable water vapor may be obtained from geodesic permanent networks, and this is actually quite good. There are different networks, and most of them are part from the GNS service. As you can see in the map, North Africa is not well covered, but you can achieve directly through national agency or institutions. We have just shown some examples, and this course map is an interesting initiative that may be useful for your project. And then I'm going to go to another thing which is also important, and there I also have a proposal that may be useful for you. This is just a report we made for the site selection of the Cherenkov telescope array. This is the Cherenkov telescope array. This is a system to measure high energy events in the atmosphere coming from high energy astrophysical things like black holes, stars collisions, active galactic nuclei. So this is a set of telescopes, open air telescopes, which have to measure such an event in the atmosphere to identify high energy things. So here you see the configuration. This is how it will be at La Palma. There are several of them because we need several of them to be able to identify better where the signal comes from at the space in the sky. But what I wanted to mention here, the first search that we did to look for, to show that the candidates were good for hosting such an installation was to analyze a long-term database of meteorological information. Here at TEIDE, at Tenerife, we have the state agency for meteorology, which I suppose there you have a similar one, has a station which are references, and there you have databases, in this particular case, for 100 years. And so we did an analysis of all these long databases. So the statistical analysis of long-term meteorological data is very important and very useful. And that we did for this. But then, soon after, we had another challenge, which was to decide where to install the future European Solar Telescope. This is the plot of the telescope. This will be a 4-meter solar telescope. As you know, a 4-meter solar telescope is a very big telescope. And then the thing is that the task we have is to decide whether La Palma and Tenerife are similar or not. And this is important because it requires to do a very accurate search, because as I showed to you before, the two islands are small, and then we need to go for high resolution data to be able to do precise study, to do precise comparison, and to give precise numbers. And then to do that, we have gone for these databases that I mentioned at the very beginning. And I think these databases are very useful. In particular, we have done, this is the two islands, Tenerife here, La Palma here, these are other small islands, these two are the highest, as maybe I didn't mention, that I mentioned now, the two observatories we have here are 2,400 meter high, and these are the red and blue are the location of the observatories. So what we did to compare these two sites in meteorological parameters, when I say meteorological, I'm thinking of temperature, wind velocity, humidity, wind direction, pressure, I mean a number of the standard parameters, and we need to have these parameters at different heights and different altitudes. So we decided to use this WERA, which is a database which uses a number of measurements, models, reanalysis. It's available to everybody. It's free, it's accessible to everybody. And these are the points of the WERA sampling. The grid of WERA is not excellent, but it's not that bad. It's 11 kilometers. And the good thing is that they have sample, they have the, let's say, data with this 11 kilometers grid point, and with a number of vertical levels from sea level to 20 kilometers high. And in this particular case, it's interesting also that the resolution, the vertical resolution is not that bad. You can sample a thickness of about 400 meters, which is not bad. So in our case, we are using this database to compare the two observatories to see which one is better to install the European Solar Telescope. Here to the right, this is a work that we did to start with, is to compare the result using this WERA database with local data, with some soundings, which are launched by the Agencia Estatal de Meteorología, Spanish Meteorology Agency, which is the reference. And so they launch 2 balloons every day, all day since a number of years. And then what we have done is to compare these profiles of the balloons launched here with the profiles obtained using WERA database. And here you have the comparison. The comparison is good. So to the right, you have the velocity, the potential temperature, the relative humidity. And so this is the work we did before deciding to use this database, which is important because, as I said, we need to be sure that the data we are going to get is reliable enough, and more important, not only that it's reliable, we have to be able to quantify the errors, and also to be able to see if there are some bias. I mean, we need to have data which are scientifically valid, and that I think we have. For instance, with this database that I said we have decided to use, we can produce things like that, the wind roses. So this is to the right, we have the site at Teide Observatory, at Tenerife, and to the right, this is the Roque de los Muchachos Observatory. So what we have done is to choose all the values from Guerra at the height of the observatories, which is 2,400 meters. For that, we have used the closest two values at the pressure closest to the observatory and make an interpolation. So like this, you can be able to produce a beautiful wind roses you have. And that we had to do during the day, because also important that in my team, we were working in nighttime values since recently, but now for the solar telescope, you need to know the performance during the day. But this you can use for the night. I mean, you have continuous monitoring of these values all over the year for a number of years, day and night, every 6 hours. And so this is a very powerful thing. With this, you can do a lot of other things. For instance, I mean, we're writing a paper on that, but here you can see something which is to me very interesting. First, you see that we are analyzing a data set of almost 20 years, which is available. So you can do that. I mean, the data set is enormous. There are a lot of data to use. I mean, you need a powerful machine, that is true, and a skilled student, that is also true, but this is something that is very useful. So here, for instance, you see the height in kilometers to the right. This is the day and the night. This is a comparison. And there you see that at the height of 12 kilometers, the wind is higher. So this is the wind velocity, right? The wind velocity. Oh, sorry, it's ORM or not. So you see that our atmosphere, we have first a temporal trend every year. You see, there are variations every year. And we have also that every year, during part of the year, the wind velocity at 12 kilometers, that is the jet stream. That is what makes the observatory to be good. But so this is something that, as I said, and I want to emphasize, you can use not only to choose in the site, but also to have, at the same time as you are choosing the site, you will have the pattern that defines the site. It will tell you what is the behavior of this particular site in the winter, in the summer, if there is a pattern, if there are some variation, and if it is stable along the years. Here you see, as I said, this is 20 years. This is a data series that you need to be sure to have before selecting. This is something I'm not going to go into detail, but with this database in the future, you can do many more things, in particular to try to identify this meteorological pattern with others, like this here to the right, which are the turbulence profiles, we have to do with the image quality. So you may be able to compare the performance, for instance, of your site in terms of the wind velocity and the image quality. That can be very useful. And this is a niche that will be open in the future if you do such a research. Again, with the help of my colleagues, we made the exercise to see how useful this Wera can be for you. This is the shadow of Wera database. And so as you see, we are here. So this is you, this is us. So we are within the view of this database. And if I do an enlargement, so this is the temperature map. We did it at 2,000 meters. So this is the temperature map at 2,000 meters. Here you have your possible, some of the places you have mentioned, they are here. So you may have, I will just show some of the parameters you can use. This is the temperature, this is the wind velocity, this is the wind direction at a given velocity. So all these numbers and many, many more you can retrieve from this database with a very accurately. So I'm almost finishing. Just something I'm just summarizing, in particular for our observatories. Now we have a number of instruments. In particular, we have scene monitors that Mark will surely tell you about and you are familiar with. These are instruments that no matter what are interesting to have in an observatory site, and if you develop one of them, it will be useful for the future to be in operation at the site you decided. We have already precipitable water vapor monitor that we call monitor, but in fact they are just software We have no hardware for that. We have just the software to get the GPS delay and to get the water vapor. We have a small that I assume that Sergio Tani will tell you about. It's important, as somebody mentioned, that the SQM are not very accurate. And although it is true that for relative comparison, they can be reasonably good, for precise values, they are not so good. And so as modes are more accurate, and I think these are necessary. We have such a thing. We have this forecasting that again is just software. It's a system which is a software. It doesn't have hardware, and this is important because like this, it's very useful to have such a tools. We have also automatic weather stations. We have now implemented the reanalysis of launch databases. We don't have extinction measurement because we had an instrument before that was the commissioning. So in the future, we are developing automatic extinction monitor, will be like small C monitors to measure extinction in a routine basis. We will update the software to get turbulence. We will do real time, for instance, this forecasting we were planning to do for turbulence. But in whatever case, what I want to emphasize that we have been learning a lot of things. We have been already implementing a lot of tools which are just based on a good programming and software and just previous calibration that we have done. And these all are useful for the new site testing and site search. And so just to finish, a simple statement, a good site to understand the universe has to be clear, dark, sharp, and dry. Identifying such a place is important, as it allows, moreover, it allows for further development of science and technology in the region. That was the case for the Canary Islands astronomy, for Spanish astronomy, and I'm sure it's going to be the case for your country. Once identified a site, still is needed to protect and knowing it better so as to implement cutting-edge technology to get them off from there for the future also. So this is very important. I mean, to me, the site characterization is something that never ends. I started that 40 years ago now, and I keep doing that and doing new things. And these new things are, they're useful to make the site even better. And that's the last thing. There are tools and instruments resulting from site testing work since nearly 40 years now, which are tested, calibrated, and can be used. So I think that we are not in a privileged situation for site selection and site characterization. Thank you.
Thank you, Cassiano. Any question? Any question? Can you hear me? Any question for Dr. Cassiano?
Yes, I can ask a question.
Yes, Dr. Yusuf.
Thank you, Cassiano, for your good lecture and for your information you give. Now we are in Egypt. We didn't decide. We are not in fully agreement about the scientific goals of our future extra large telescope. So, as I know from your lecture now, the one parameter is perceptible water vapor is deciding about some instruments that we are going to install in our telescope. So what we are not now in full agreement about the scientific goals of our telescope. So how can we decide about the scientific goals of our telescope as long as we didn't measure any meteorological data till now? We are now in the part of deciding the scientific goals of our telescope. What's the instruments that we are going to install or are going to, apart from the budget, of course, but we need to have a telescope that will benefit from most of the astronomical observation. So how can we decide about scientific goals of our telescope as long as we didn't know about the meteorological parameters that we are going to do in the future in the site test fields?
Okay, I think that you have your project is challenging because you want to do everything at once, because we could do, I mean, one possibility could be just for you to explore what is the scientific interest for your community and then go for the needs of your community. But I think that if you're thinking an optical telescope, no doubt, I think you have to include a near infrared instrument in an optical telescope. So an optical telescope should include the infrared, because otherwise you are very limited in the study of the universe. You know, I mean, you know better than I. So to me, I would say that optical would mean optical and near infrared. I cannot understand an optical telescope stopping at 1,000 angstroms. I mean, to me, it's not. I wouldn't. It has no sense. I mean, you have to include the near infrared. Otherwise, I mean, you have to get. You know, I mean, the peak of the star formation in the universe is at set 2. So you have to be able to catch the lines. I mean, you have to be able to measure these galaxies. So optical to me would be to go to the near infrared at least. And that should be the case, the water vapor is more important. And as I have mentioned this, I think this is something which is relatively easy to do, because much of the work for calibrating is already done. I mean, we have devoted a lot of time to demonstrate that it can work. And therefore, you just need to implement the tools and to do the homework, I mean, the programming and that. So once you decide that it's an optical near infrared telescope, which particular instrument, this is also an issue, which is also, I mean, nowadays, you have two possibilities to go to very, I don't know what to say, to go to simple instruments, easier instruments to build, depending on whether you want to do it at home or you want to go. And that would be sensible to go for instruments which are not too complicated, because otherwise the program, the project can be unfeasible at the end. And so not too complicated. For instance, a prime camera, prime focus camera is too complicated to get a good imager. A wide field camera is a very complicated instrument, although it is very exciting. I mean, we all astronomers want to have a wide field camera, but this is very complicated to have. But I'm saying something, I mean, I think that if you want, we have, Jose Miguel will talk tomorrow, that as you know, he was the project scientist of the GTC, of the GTC, of the 10-meter telescope. Your opinion will be certainly very, very sure. But myself as astronomer, I think that an optical near infrared telescope would be the name of the telescope. The size, I don't know what is the size, but a 4-meter size is a reasonable size. And the instrument, spectroscopy is something that needed to be done. And also this spectroscopy, now there are tools for doing multi-spectroscopy, which is relatively easy. But in any case, for site characterization, the issue is to have, first, the clouds have to be absent. I mean, the percentage of useful time has to be more than, say, 60, 70%. So this is a crucial parameter, the cloudiness. This is important. The variation, the long-term variation, so you need to be sure that the things you are taking now are going to remain good in 1 year or in summer, or so the seasonal trend is important to know, you need to know. The possible effect of Saharan dust is also very important. Less important the higher you go, but then you have to be sure to see at what height the dust remain when there are such dust events. And the dry of the sky is also important. And also, and the darkness, again, as I said, it is very important. And if you define a site because it is dark, you have to push a regulation that assures that in 10 years from now, this site is going to be dark. I mean, that you don't have to move again. Because, I mean, that have to be assured. Because otherwise it's a waste of time and investment. I don't know. I mean, if you want, we can talk. I mean, there are many arguments to decide, which is the possible argument to decide about your telescope. I mean, something is. I mean, I can just. I don't know. I don't know.
Thank you.
Thank you, Professor. Any more questions? Any more? Okay. The next talk, Dr. Mark Sarazin, European Southern Observatory. Dr. Mark Sarazin.
Hello, good morning, everybody.
Hello.
So thank you for the invitation. I'm very happy to see my colleagues. Cassiana, hello, long time no see. And, I think the three talks you have chosen are very complementary. Cassiana has really insisted on the possibility of a water vapor. I will not talk too much about it. And then the next talk is a lot about atmosphere, so extinction, which I won't address either now. So it's a very good organization, my dear Zoe. Good, I will share my screen and I hope it will work. Search, do you see something? Okay. Do you see my slides?
No.
Yes.
Let me see. So maybe this one.